In this video, we will take a closer look at trigonometric functions defined by geometry, by right triangles, and we'll introduce the tangent function as well. We've already said that for an acute angle theta on a right triangle, sine of theta is the ratio of the opposite leg to the hypotenuse of the triangle. Cosine of theta is the ratio of the adjacent leg to the hypotenuse. And now, our new function, tangent of theta, is the ratio of the opposite leg to the adjacent leg. Here's a diagram that shows for an angle theta, the opposite, adjacent, and hypotenuse. Remember that these terms opposite and adjacent leg are relative to where the angle is located. So the opposite leg is the leg directly opposite from the angle, and so on. Some people learn a saying in high school to help them remember the trig functions, SOHCAHTOA. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent, or SOHCAHTOA. If that is helpful to keep these ratios in mind, you're welcome to use that analogy. I want to say a bit about tangent of theta. So we've said that tangent of theta is the same as opposite over adjacent. Now we could imagine saying that it's also equal to opposite over hypotenuse divided by adjacent over hypotenuse. And by writing it in this form, we have transformed tangent theta in terms of sine and cosine. Opposite over hypotenuse is sine, adjacent over hypotenuse is cosine. So we can express tangent in terms of sine and cosine. Tangent is sine theta divided by cosine theta. This is helpful if we're working with trigonometry on the unit circle. On the unit circle, remember that sine theta is the y value, cosine theta is the x value. So tangent theta is y divided by x for a point xy on the unit circle. It's a little bit tedious to calculate tangent using the unit circle because it's a ratio of the two values, but it is possible to do it. And we begin to see here that there must be some limits on the domain of tangent. If we're thinking of it as y divided by x, it would be undefined, or wherever the x value is 0. We'll explore that more when we look at the graph of the tangent function. So let's consider a couple of examples for how we can use right triangles to find trigonometric expressions. Here we're given a triangle and we want to find the following values. Sine of A. So sine of A is the opposite over the hypotenuse relative to the angle A. Opposite leg would be 2, hypotenuse would be 3. So sine of A equals 2/3. Cosine of B is the adjacent leg to B divided by the hypotenuse. Adjacent leg to B is 2 and the hypotenuse is 3. So we're seeing here that sine of A and cosine of B are actually the same thing for angles A and B on the same triangle. Tangent of A is opposite over adjacent relative to the angle A. So it would be 2 over square root of 5. If we want to rationalize this answer, I would multiply by the square root of 5, and I would express our answer as 2 root 5 over 5. Tangent of B is opposite over adjacent relative to the angle B. So the opposite leg to B would be square root 5, the adjacent leg would be 2, and we have root 5 over 2. In our next example, we're given a value of cosine theta. So suppose cosine theta equals 3/5 for an angle theta in quadrant 4. This is important because this says something about the positive or negative sign of our sine and cosine and tangent values. we are looking at an angle in quadrant 4. It's not an acute angle anymore. It has all the same sine, cosine, and tangent values as its acute reference angle, with the exception of positive or negative signs. So in quadrant 4, as we discussed earlier, cosine is positive, sine, which is the y value for a point, is negative, and because tangent is sine over cosine, tangent must also be negative. It's a negative value divided by a positive value, which makes it negative. So from this point on, I could set up a right triangle to solve this problem. I just need to remember that in the end, sine of theta is negative and tangent of theta is also negative. Here's a sketch of what is going on using the acute reference angle. So we have theta, cosine of theta equals 3 over 5. So the adjacent leg should be labeled as 3. The hypotenuse should be labeled as 5. And we can use the Pythagorean theorem to find the remaining leg. We can say 3 squared plus x squared equals 5 squared, or 9 plus x squared equals 25. Subtracting 9 from both sides, we get x squared equals 16. Therefore, x equals 4. So our remaining leg here is 4. And in fact, the numbers 3, 4, and 5 make what is known as a Pythagorean triple. They are integer numbers that fit the Pythagorean theorem. So now that we have these values, we can label sine of theta and cosine of theta. I need to remember to make sine of theta negative, and so it would be opposite over hypotenuse. We're going to say it's negative 4 over 5. And I also need to make tangent of theta negative. Opposite over adjacent would be negative 4 over 3. Here are our final answers for sine and tangent of this angle.